Okay, yeah. So I want to first ask you, what do you want to do first? Do you want me to go through everything in the topic, like a revision, and then do some problems, or do you want me to straight away jump to the problems or the past paper questions, whichever you like? What do you want me to do?
Maybe you can do some exercises.
Exercises from the textbook. Okay. Well, we can do some exercises from the textbook, and we can do some past papers. So let's do 4.1.1. So let A be equal to A, B, C, B be equal to 1, 2, 3, which are the following subsets of A cross B or functions A to B. So now you tell me. So it's 1, 2, 3, and A, B, C. So A is this, B is this. And we have B1, C2, A3. So first of all, for each element in A, we're only going to one element in B, so this is a function. For this one, this does not cover all the elements because C is not going anywhere, then this is not a function. Then for this one, A is going to 3, C is going to 2, A is going to 1. Now over here, A is going to 1 and A is going to 3, so this is not a function. So remember these rules. These are important, especially like when you go forward in doing mathematics, you will not see an example like this as often as you see an example like this. So sometimes you have to prove what a well-defined function is in the examination. If you're trying to say that two functions are bijective, or you're trying to prove a property about a function, you have to prove that a function is well defined. Well defined. Well, how do you do that? The way you do that is you take some A, and then say A belonging to A. If like the function is from A to B, you're trying to prove that this is well defined. Take some A belonging to A, and then assume that for some B, A is equal to B, and then you argue. You do some argumentation, and then you basically get the result FA is equal to FB. So what this proves that if one element will only go to a unique element in B. And most of the time, this is extremely straightforward. You can just skip the proof, but especially for this semester, if they ask you to prove that the function is well defined, you have to do something. You have to do this. So remember this. I think 4.1.1 is fairly easy. I don't need to do more of it. But okay, yeah, let's do this. Which of these diagrams represent functions? So does number 1 represent a function? Yes, because for each element, we're going to a unique element in B. And I do not mean that for each element we're going to a different element in B. And I'm just saying for that specific element, we're not going to more than one element in B. So yeah, that is proper. And for every element, we're going to some element. So we don't have a problem here. Both conditions are satisfied. This is a function. For the second one, the condition that the whole set is covered is satisfied, but one element is going to two elements, which is not possible in a function. So this is not a function. For the third one, this is not a function because the whole set is not covered. For the fourth one, this is a function because the whole set is covered, and one element is only going to one element in F. Also, by the way, the Other way around is fine. It's just it's possible to have a function that is something like 1, 2, 3, and over here we have 1, 2. It's fine to have a function like this. This is a function, but if this was our original set, this is not a function. Which of the following formulas define function R to R? Okay, let's do this one. So f of x is equal to sine x for all x belonging to R. So first of all, is this function properly defined for all x? For given any x in R, can we find sine x? Yes, we can. And given any x in R, is the value of sine unique? Yes, it's unique. If, let's say, x is arbitrary, sine of x cannot have two values. So yes, this is a proper function. Now for p of x, x squared plus 3 over x plus 5 for all x belonging to R, is this a function? This is not a function because minus 5 cannot go anywhere. This operation is not defined for minus 5. So it's not a function for x belonging to R. This is, however, a function for x belonging to R minus 5. So if you just remove that element from R, you will have a function, a valid function. The third one, qx is equal to ln of x to the 4 plus 1 for all x belong to R. So first of all, let's think about this. For all x belonging to R, is this defined? So if any value of x will be greater than or equal to 0 over here, any value of x over here would be greater than or equal to 0. So this would be greater than or equal to 1. And we know that ln of 1 is defined and ln of bigger than 1 is also defined. So this covers all x, and for each x, it does have a unique value. So yes, this is a function. I think you can do the rest. Let's just do g of x for fun, number 7. So g of x is equal to sine of x if x is greater than or equal to pi, and g of x is equal to x if x is less than pi. Do we have a problem with this function? Since sine of x is defined over all x, we know it's defined over x is greater than or equal to pi. Also, we know that since x is defined over all x, x is defined over x is less than pi. We have no problem with that. And each of these functions obtain unique values. Also, an example here, if this was x is less than or equal to pi, we would have a problem because the function might take two values, and we don't want that. And then for some x, the value will not be unique, and hence it will not be a function. But right now, this is a perfectly valid function. Okay. Do you have a specific exercise, by the way, that you want to do?
Can we do the 7?
Number 7, 4.1.7?
Yes.
Okay. So let A and B be sets. S is a subset of A, and let f of A be a function. G of A be an extension of f to A. does G equal F? Give a proof or a counterexample. So first of all, let me just take a photograph of this. Okay, so S is a subset of A here, and we know that F of A, B is a function, so it's defined, it follows all the properties of a function. And G of from A to B is an extension of, I think there's something wrong with the function over here, because when they say extension, this should have been F that goes from S to B, I believe, not from A to B, right? Right? I think there's a mistake there or something. Let me just check the definition of extension. So if G of from S to B is a function, an extension of G to A is any function G from A to base B such that G of G by S is equal to G. So yeah, over here I think it was supposed to be F from S to B, because this does not really make sense, right? Any answer, opinion? So we have a function that goes from S to B, and F S and G is an extension of F to A. So G is an extension. Actually, this can still be true. This can still be true. So if F is going from A to B and G is again a function from A to B, then the extension of F of S to A. So we're only looking F by S. We're only looking at that specific part. So F by S is this function. F by S is this function that goes from S to B, and we're trying to find that does G equal F, and this is clearly not true, because let's try to construct this. Let's say we have, I'm not going to write it down very rigorously here, I'm just going to give you the idea because otherwise it will take a lot of time. So let's just think about this. Let our original function be y is equal to x. So our function over here is it goes from real numbers to real numbers, and this just takes an x to x. So for each x, so f of 1, for example, is equal to 1. You have seen this in 153 probably. It's a very basic function. So it's something like this. And let's say our subset of the rational number, let's say S is equal to the closed set from 0 to 1. So it is all the values between 0 and 1, including 0 and 1. So let me draw it over here. This is our subset. And now we're considering the f by s function. So we have f by s. I will denote it in blue over here. F by s, that will go from s to b. B again over here is the real numbers, and from s to r. Let me write it properly. Yes. So this function is just the part of f that acts on the subset s. So it's just this part, this function over here. It's going from 0 to 1 to the real numbers. So this function. And what if, and here's the tricky part, what if we consider the function g, consider g such that, consider g that goes from real to real, such that g of x is equal to x if x belongs to the interval 0 to 1, and it's 0 otherwise, right? This looks like a fairly normal function. This is, if you want to check it's well defined, then for each, this first of all covers all the real numbers. There's no problem with that. And for each x value, we're going to unique value in r. We're not going to two different values. Then we have this function. So we have this function. It acts like 0 over here, and it continues being 0 after. But is this function equal to f? No, it's not, because let's say we take an element pi, and for pi, g of pi is equal to 0, but f of pi is equal to 1. Hence, f is not equal to g, and we're done. So did you understand the proof? This was a counter example, but it was explained rigorously. Do you understand the solution?
Yes.
Okay. What's the next problem you want me to do? We can do it from the next section as well if you want. Anyone? What question do you want me to do?
A minute.
I'm sorry, what? I was not able to hear you.
I'm finding. I'm searching for
Okay.
the hardest one.
Okay. I think I highlighted this one, so it must have been hard. Like, these are my highlights from when I was studying Math 111. So these are not new highlights. So this should be a fairly difficult question.
Okay, we may do this one.
The characteristic map. So first of all, you have to understand this function. I will try to do as much as I can in the 7.5 minutes left, and then I will send a new meeting link to the group. So let X be a non-empty set, and let S a subset of X be a subset. The characteristic map for S in X, denoted by the curly excess, let's just call it excess for now, is the function that is from x to 0, 1 defined by x of s is equal to 1 if the element belongs in the set, in the subset, and x of s of y is equal to 0 if y belongs to the complement, or it does not belong in that set. Now let E be subset of X. Prove that the characteristic map of A is equal to the characteristic map of B if and only if A is equal to B. Observe that this is a statement of equality of functions, whereas this is a statement of equality of sets. So let's write this down. So we have a characteristic map. Characteristic map XS that goes from X to 0, 1, and it's defined by it's defined like this. So excess of y is equal to 0 if y belongs to x minus s, 1 if y belongs to s. So this basically tells you that whether an element is in the set or not. So assume that x of A is equal to x of B. We will try to prove this direction first. So assume that x of A is equal to x of B. So let's take an arbitrary element A. Let A belong to A. And what do we know about this? We know that this is an A, so hence, by the definition of characteristic map, by the definition of the characteristic map, x of A is equal to 1. But we know XA is equal to XB because by our assumption. Now, what does this mean? This means that x of B of A is equal to 1 as well. But this is only true when A belongs to B. Hence, notice again, we have what have we started with? We have started with an arbitrary element in A, and by our argumentation, by everything we know, we've come to the conclusion that it is also an element in B. Hence, A is a subset of B. Okay, this is good. And similarly, by a similar argument, you can just change everywhere I wrote. Over here, you can start with let B belong to B, hence by the definition of the characteristic map, xB of B is equal to 1, but we know XA is equal to XB by our assumption. So XA of B should be equal to 1, but this is only possible when B is in A. So similarly, you can just, I'm just gonna skip that part. So similarly, we can show B is a subset of A, right? And what does this mean? This means that A is equal to B. So we're done with one part of our theorem. We're done with one direction. Now, let's look at the other direction. Let A be equal to B. Then we know for the characteristic maps of XA and XB, we have equal domains by our assumption and equal codomains by the definition of a characteristic map, of a characteristic map. What do I mean by this? By the definition of a characteristic map, if you remember, the characteristic map is defined like this. It goes from X to 0, 1. But what does this mean? This means that this part is same for all characteristic maps. So this is same for any set X. So we know these functions have equal domains and codomains. So